이번 동영상부터는 Discrete Kalman filter에 대해서 시작하도록 하겠습니다. The Kalman filter operates by propagating the mean and the covariance of the state through time. We start with a mathematical description of a dynamic system whose states we want to estimate. We implement equations that describes how the mean of the state and the covariance of the state propagate with time. We take a dynamic system that describes the propagation of a state mean and the covariance and implement the equations on a computer. These equations form the basis for the derivation of the Kalman filter because A. The mean of a state is the Kalman filter estimate of the state. B. The covariance of the system is covariance of a Kalman filter state estimate. Every time that we get a measurement, we update the mean and the covariance of the state. Derivation of the discrete-time Kalman filter에 대해서 알아보겠습니다. Suppose we have a linear discrete-time system given as follows: fk, sk equal fk minus sk minus gk minus uk minus wk minus yk는 hk, sk, vk인데 여기서 noise process wk and vk are white, zero mean, uncorrelated, and have known covariance matrices qk and rk respectively. wk가 normal distribution mean이 제로 벡터하고 covariance가 qk. vk도 normal distribution의 mean은 제로고 covariance matrix. 여기서 independent 하다는 거 보여주는데 델타 k j는 크로네크 델타 펑션, that is kj가 1이 되는 거는 kj 같을 때고 다르면은 0이고, 그죠? 요거는 서로 독립이라는 걸 보여줘도 서로 노이즈끼리. Problem. Our goal is to estimate the state xk and on our knowledge of the system dynamics and the availability of the noise. Our goal is to estimate the state xk based on our knowledge of the system dynamics and the availability of the noise measurement. YK는 이제 noise measurement죠. If we have all the measurements up to and including time k available for use in our estimate of xk, then we can form a posterior estimate which we denote as sk hat plus. The plus superscript denotes that the estimate is a posterior. One way to form a posterior state estimate is to compute the expected value of sk conditioned all the measurements up to and including time k. sk 플러스는 yk까지 포함하는 the posterior estimate. If we have all the measurements before but not including time k available for use in our estimate of sk, then we can form a priority estimate which we note as sk hat minus. The minus superscript denotes that the estimate is a priori. One way to form the priori state estimate is to compute the expected value of xk conditioned on all the measurements before, but not including time k, yk minus 1까지 포함한 a priori estimate. We naturally expect xk plus to be a better estimate than xk minus because we use more information to compute xk plus. xk minus estimate of sk before we process the measurement at the time k. sk plus estimate of sk after we process the measurement of time k. If we have a measurement after time k available for use in our estimate sk, then we can form a smoothed estimate. One way to form the smoothed state estimate is to compute the expected value of sk conditioned on all of the measurements that are available skk plus n. k plus n, the smoothed estimate. where n is some positive integer whose value depends on the specific problem that is being solved. If we want to find the best prediction of escape more than one time step ahead of the available measurement, then we can form a predicted estimate. One way to form the predicted estimate is to compute the expected value of escape conditions on all the measurements that are available. K minus predicted estimate, where m is some positive integer whose value depends on a specific problem that is being solved. The relationship between the posteriori, a priori, smoothed, and predicted state is depicted in figure 1. A posterior estimate, or priori estimate, position estimate, smoothed estimate. Figure 1, timeline showing the relation between the posterior, prior, smoothed, and predicted state estimate. In this figure, we suppose that we have received the measurements at time up to and including k equal 5. An estimate of the state of k less than 5 is called smoothed estimate. An estimate of state at k equal 5 is called a posterior estimate. An estimate of state at k equal 6 is called a priori estimate. An estimate of the state of k larger than 6 is called prediction. In the notation that follows, we use x0 first to denote our initial estimate of x0 before any measurements are available. The first measurement is then taken at the time k equal 1, since we do not have any measurements available to estimate x0. It is reasonable for form x0 plus as expected value of the initial state x0. We use the form pk to denote the covariance of the estimated error. Pk minus is the covariance of the estimated error of xk minus 1. Pk plus 1 denotes the covariance of the estimated error of xk plus. Pk minus Pk plus. These relationships are depicted in figure 2. The figure shows that after we process measurement at time k minus 1, we have estimated xk minus denote xk minus 1 plus, and the covariance estimate denote pk minus 1 plus. When the time k arrives, before we process the measurement at time k, we compute the estimate of sk denote sk minus, and the covariance of the estimate denoted pk minus 1. Then we process the measurement at the time k to define our estimate of sk. The resulting estimate of sk is denoted sk plus, is covariance denoted pk plus. Sk minus plus pk, sk minus 1, sk plus pk minus 1, pk plus 1, pk minus 1. Timeline showing a prior and the posterior state estimation and estimation error covariances. We begin the estimation process with x0 plus, our best estimate of our initial state x0. Given x0 plus, how should we compute x1 minus? We want to set x1 minus ex1, but note that ex0 plus ex0. Recall how and the mean of x propagate with time. sk irradiation. Then where x is irradiable. Equation 16 is a specific equation that shows how to obtain x1 minus from x0 plus. However, the reasoning can be extended to obtain following more general equation: sk minus and fk minus sk plus, sk uk minus 1. This is the time update equation for x. From time sk minus 1 plus to time k minus 1, the state estimate propagates the same way that the mean of a state propagates. sk minus 0 and sk minus 1, fk sk minus 1 plus uk. This makes sense intuitively. We do not have any additional measurements available to help us update our state estimate between the time k minus plus and the time k minus 1. So we should just update the state estimate based on our knowledge of the system dynamics. Next, we need to compute the time update equation for P, the covariance of system estimate error. We begin with P0 plus, which is the covariance of the state estimate error. If we know the initial state properly, then P0 plus is zero matrix. If we have absolutely no idea of the value of x0, then P0 plus infinity matrix. In general, P0 plus represents the uncertainty in our initial estimate zero. 이렇게. Given P0 plus how we can put P1 minus 요거는 다음 동영상에 올리도록 하겠습니다. 감사합니다.